Assalamualaikum and a very good day to all of you. Right? So, I'm Shikin Aziz, and now we move to the next topic on high pressure and liquid storage tanks. So, this topic cover under process equipment design, a course for undergraduate student of Bachelor of Process and Food Engineering in Universiti Putra Malaysia. So, So for high pressure tanks, okay, there are many application in industry out there will need you to design high pressure tanks. Basically, there is no recommended upper limits on pressure. All right. So, but SME BPV code, okay, SME BPV code section 8, division 2, they provide rules, okay, the alternative rules to design high pressure tank which operate above 2000 psia, where the alternative rules provided in the standard is selection of materials, allowable operating temperature, which is less than 482 degrees Celsius, and provide strict requirement on stress analysis and testing. So this division 2 allow higher maximum allowable stresses and hence lead to thinner wall vessels. Then SME BPV code section 8 division 3 provide a rule for design pressure vessel above that working at above 10,000 psia or 680 bar. Okay. So you need to bear in mind, okay, when it comes to high pressure vessels, all right, the design will become increasingly difficult, okay, because the fabrication will require extra, okay, extra specification, right? For example, uh, among the method that been used to increase the strength of the vessel wall is by using compound vessel technique. So the compound vessel, there are three types. Okay, three types of compound vessel. One is shrink-fitted cylinders. Two is multi-layer vessel, and third is wound vessel. So for shrink-fitted vessels, it's made by shrinking, okay, by shrinking one cylinder over another cylinder. Okay, there are two cylinder here. Okay, if you can see here for this illustration where I taken from this website. All right. So the inside diameter of the outer cylinder, okay, the inside diameter here, the inside diameter of the outer cylinder. Sekejap, hold on, for somehow I cannot uh, open my what do you call it? Is it? There is. Oh, sorry. Okay. It's okay, just ignore that. So, the inside of the outer diameter is made slightly smaller than outside diameter of the inner cylinder, and then is expanded by heating to fit over the inner. That is how it been insert into the that is how fabricator insert the inside tube into the outside tube, something like that. All right. And then on cooling, the outer cylinder contracts. Okay, the outer cylinder contracts and places the inner under compression. So the stress distribution in two cylinder compound like this vessel is shown in this. Sorry, this sorry. So does uh, offset the during by doing this. Okay, by doing this. The offset that it can offset the tensile forces that will act most strongly on the inner layers during the operation. Okay. All right. Then let's look on the multi-layer vessel. Okay. I couldn't find another example uh, of photo, a good photo to represent the multi-layer vessel. And this vessel is taken from Towler and Synod textbook. Oh, by the way, another thing that I need to add up for the shrink-fitted cylinder. Shrink-fitted compound cylinder are normally used. This technique are normally used for small diameter vessels such as compressor. Okay, this is normally being used for small diameter vessel. And then for multi-layer vessel here, okay, is actually made by wrapping. Okay, if you look at this diagram, is actually there are several layers, okay, of a metal plate. So by wrapping several layers of relatively thin plate round a central tube. So the plates are heated, tightened, and welded. Okay, welded in the structure here, around the structure here, and then with this fabrication, it gives the desired stress distribution in the compound wall, around this compound wall. So and then the vessel is closed with a fork head. All right. So there are detail on this. Okay, you may refer another reference and as been suggested in your textbook. Please refer your textbook. Okay, textbook of chemical engineering design, principle and practice. Then third technique is wound vessel. Wound vessel. For the wound vessel, the cylindrical vessel will be reinforced by winding. Okay, by winding. Okay, like this. This is technique of winding. All right. There are several type of winding technique. Okay, there are several type of winding technique actually. So this is known as helical winding, and then this is known as hoop winding. Right, and then this one I forgot the name for it. Sorry for this. There is a name for this. I think I don't know. Not so sure. This is not helical. There's another type. All right, and then uh, so it will reinforce by binding on wire or thin ribbon. Sometimes they are using reinforced fiber. All right. So winding on the wire under tension places the cylinder under compression. For high pressure vessels, special interlocking strips are used such. All right. So some of the design here it has interlocking. So the strip may be wound on hot to increase the pre-stressing. Okay, so you may refer other reference for detail on this. Okay, but you must know that you are process engineer are not onto the metal reinforced technology. Is that is under field of mechanical and material engineer. Alright, so this is just to create your awareness. Okay, to give you some fun, just a surface knowledge on this technology, so that you can consider, you can specify in your design project. Alright, class. Now, okay. So then let's look another technique. Okay, this is not under technique of technology. Uh, okay, is not under category of compound vessels. Techniques is known as autofrettage. So autofrettage is a method to pre-stress the inner part of the wall of a monoblock vessel or tuber, okay, to give a similar stress distribution to that obtained in shrink-fitted compound cylinders. But the only difference is shrink-fitted compound cylinder have two layers, but this one is actually one layer. But for the inside of the layer, all right, inside layer, sorry, for the inside of the vessel body or vessel wall, uh, there is a compressive, there is a process has been done inside of the vessel or inside or on the wall. Okay, so where during this process, it's over pressurized by hydraulic pressure, actually. So during this process, the inner part of the wall will be more highly stressed, all right, than the outer part. So this is before, this is during autofrettage, and then this one is after autofrettage. So after autofrettage, you should be expected that the inside wall will be high compressive, all right, compared to the outer wall. Okay. So during the process will undergo plastic strain. So so for this, uh, for this type of technology, the vessel can be used at pressure up to the outer frettage pressure. Outer frettage pressure, without permanent distortion. So I'm not so sure. I haven't checked what is the outer frettage pressure. Alright, but this one is can be checked later on if you would like to consider this technology. If you want to specify this technology in your plant design project. Okay. Then now let's look on liquid storage tanks. Okay. So common design at atmosphere pressure, vertical cylindrical tanks will be considered, and with a flat base and then conical roof. Okay, and then the tank size may be vary from tens of cubic meter to several hundreds cubic meters. All right. Then the main loads to be considered in the design of liquid storage tank is the hydrostatic pressure, and then there is also other loads need to be considered, such as it can withstand wind or weight of snow. If let's say you are designing a factory at Four Season country, then uh, the minimum wall thickness, the minimum wall thickness can be calculated by using this expression, where for this expression, this term TT is tank thickness at depths of HL, where HL is liquid depth. And then you need a liquid density, where for here the liquid density is recommended to use water, all right, density. But if let's say your process liquid density is bigger, you need to use the process liquid density, which has bigger density. Then G for gravitational acceleration, and ST stand for maximum allowable stress for tank material. Alright, this depending on the tank material, and you need to refer the standard. And then DT is the tank diameter. So normally constant thickness will be used for small tanks, okay? And the calculation for this you need to consider at maximum liquid depth. All right, the condition at maximum liquid depth. And then plate thickness will be gradually increased from top to bottom of the tank if you are designing a bigger tank, a big tank, a large tank. All right. All right. For detailed calculation of this design of liquid storage tank, you may refer American Petroleum Industry Standard API 650 and 620 for atmospheric storage tank for petroleum liquid, alright, material or a petroleum for a petroleum application. While if you can refer European Standard BSEN 14015 for metal tanks, while BSEN 13121 for glass reinforced polymer tanks. Alright, so there are several standards you can refer depending on the applications. Alright, for liquid storage tanks. Okay, so that's it for now, class, for this topic. Alright, so we shall meet again in the future with other recorded video lecture. Okay, see you again. So hope you this lecture note can give you some insight of uh, vessel design. Alright, alright. Bye. Assalamualaikum.